In the name of God, the Compassionate, the Merciful. I am Abdullah Dusti Aref. This presentation is related to part of my research effort in which some challenging issues concerned with propagation of acoustic waves over underwater acoustic channel are addressed. The title of this talk is Tuning the Franquist and Garrison Formula, or TFGF algorithm, which addresses a simple method for tuning the parameters of absorption coefficient formula in the seawater based on the experimental measurements of any interest region. At the first, to show the necessity of more investigation about the underwater world, I would like to emphasize to this fact that nearly 71% of the Earth's surface is covered with water, and 97.5% of it being seawater. This vast underwater world is extremely rich in minerals and oil resources, which today, because of the technological advances, we are able to exploit them. In recent years, design and implementation of efficient underwater acoustic systems have been receiving an increasing attention in both military and civilian applications. One of the most challenging features of underwater acoustic channel, in comparison with its terrestrial radio frequency counterparts, is highly frequency-dependent path loss. In order to design and analyze sonar and underwater acoustic communication systems, utilizing suitable model for propagation loss leads to more promising performance. In this context, this presentation addresses a simple method for efficient modeling of the absorption loss in the seawater based on the experimental measurements of any interest region. Transmission loss in underwater acoustic channel mainly includes spreading loss, absorption loss, and scattering. In shallow water channels, scattering is mainly due to the reflections from the bottom and surface of the sea. This presentation focuses on the absorption loss, which is the most important factor that distinguishes transmission loss in underwater acoustic channel from terrestrial radio frequency channels. The attenuation of absorption is due to the changing of acoustic energy to the heat. In literature, absorption coefficient is a function of frequency, temperature, salinity, pressure, and acidity. Moreover, we must consider the viscosity of pure water, relaxation of boric acid, and especially relaxation of magnesium sulfate mainly contribute to sound attenuation at frequencies 10 to 100 kHz. There are several empirical formulas for absorption coefficient. Although empirical models are useful, they result in suitable performance merely in the regions from which they have obtained. Therefore, it is not efficient from an engineering standpoint to utilize empirical models where there is a significant difference between the experimental data of an interest channel and the output of empirical models which have not obtained from that channel. However, tuning and modification of classic models based on experimental measurements and utilizing modified models leads to better performance in the appropriate interest channel. In this context, this presentation addresses a new algorithm, including general steps for parameter tuning of a widely used formula based on the experimental measurements which can be simply acquired from an interest region. As listed in the table, several empirical formulas have been introduced for the absorption coefficient. Amongst them, the most comprehensive one belongs to Franquist and Garrison, which is referred as FG henceforth in this presentation. FG formula is generally used as a standard. Franquist and Garrison verified their observations by measured data in various geographical regions under different scenarios. Due to the generality of FG formula, other researchers based it and derived some simpler formulas. However, their simplicity is not gained at the expense of the accuracy, as Van Mull reported in his valuable research effort. In this context, this presentation addresses a simple algorithm, including general steps for tuning the parameters of FG formula in the frequency range of 10 to 100 kHz, while the appropriate sound speed profile and experimental data of each interest region can be utilized. The tuning procedure presented here is much simpler than other methods, since no inverse problem is defined and consequently no exhaustive search is needed. It should be noted that our proposed algorithm results in a tunable formula for the absorption coefficient without considering any specific situations. Therefore, one can utilize it along with the required experimental data of any interest region to obtain an efficient formula for that region. In this section, a simple algorithm is addressed for tuning the parameters of FG formula in the frequency range of 10 to 100 kHz. According to FG formula, absorption coefficient in dB per kilometer is given by equation 1. In this formula, the parameter f denotes the frequency in kilohertz. The parameters AI are the temperature and salinity dependencies in centigrade and part per thousand respectively. Similarly, the parameters Pi are the depth dependencies in meter, and the parameters Fi are the relaxation frequencies. Meanwhile, the contribution of boric acid, magnesium sulfate, and pure water are respectively quantified by both AI and Pi parameters. In this figure, the absorption loss of each factor based on FG formula as well as the overall absorption loss are depicted in terms of frequency. As obviously seen, in the frequency range of 10 to 100 kHz, the total absorption coefficient becomes equal to the absorption coefficient of the magnesium sulfate. Therefore, because of the extra low contribution of other two terms in the aforementioned frequency range, without missing none of the environmental parameters, equation 1 is properly simplified to equation 2. Hereby, we should merely tune the parameters A2, P2, and F2 in a manner that equation 2 be fitted to the appropriate experimental data with a fine accuracy. According to the FG formula, the parameters A2 and F2 are functions of temperature and salinity, whereas the parameter P2 is merely dependent on depth. Our strategy is that the variations of temperature and salinity efficiently show themselves in the related sound speed profile of the interest channel, which should be utilized in the appropriate model. Therefore, in the tunable formula which is presented for the absorption coefficient, we consider the parameters A2 and F2 similar to FG formula. However, a new modified function should be obtained for the parameter P2 by utilizing the appropriate experimental data at each depth of the channel. In experimental tests, we need to find the absorption coefficient at different depths of the channel under the related conditions of temperature and salinity which form the sound speed profile of the interest channel. Therefore, by utilizing the experimental data related to temperature, salinity, sound speed, and attenuation coefficient, the values of parameter P2 is first computed at each depth by equation 3. At last, by knowing the values of parameter P2 at each depth, one can do a suitable fitting such as least mean square error curve fitting to express the parameter P2 as a function of depth. According to the mentioned modification steps, TFGF algorithm is proposed as a simple method for tuning the parameters of FG formula. Based on this algorithm, adaptive modification can be simply done through offline processing in underwater acoustic systems. In TFGF algorithm, all essential inputs, including the appropriate sound speed profile and the values of absorption coefficient, can be simply provided via a sonar subsystem. In this section, the performance of proposed algorithm is evaluated based on the experimental data. A Strait of Hormuz, owing to its abundant oil and gas resources, is militarily, economically, and politically a strategic region, which is known as a shallow water channel worldwide. During the period from December 2014 to June 2015, extensive sea experiments were conducted in the Strait of Hormuz by Iranian experts. The location of experiment site along with its borders are illustrated in this figure. The main goal of the experiments was first to find the source regions of dense water formation that derived outflows, and second to measure some channel characteristics such as salinity distribution, temperature salinity profile, absorption loss, and ambient noise. Both passive and active sonar subsystems were employed via submarine to acquire the appropriate experimental data. The active sonar was bow-mounted, and the passive one was hull-mounted. As illustrated, the water depth around the experiment site was variable from 50 to 105 meters. The distance between the borders B1 and B3 is 43.03 kilometers, and the distance between B2 and B4 is 32.63 kilometers. Experiments were carried out at different days from December to June as well as at different times of a day under different scenarios. It should be noted that the average values of experiments are used in this work. To evaluate the performance of proposed algorithm by experimental measurements, the average value of 3,000 samples is utilized at each depth for computing the parameters such as temperature, salinity, and absorption coefficient. It is worthwhile to point out that due to large seasonal variations in the temperature and salinity, changes in the seasonal pattern of sound speed was evident from December to June. Unlike what was observed in both autumn and spring, namely considerable decrease of sound speed from surface to bottom, vertical sound speed profile increased from surface to bottom and had negligible changes during the winter. In this study, we utilized the approximate sound speed profile presented in reference 2 for the Strait of Hormuz and the related calculations. To measure the absorption loss at an arbitrary depth, different carrier frequencies were utilized, while the related temperature and salinity of water were simultaneously recorded via individual sensors. Each experiment was recorded during 5 hours. During an hour, 600 samples were acquired. In other words, the channel was captured 10 times a minute. As a result, the number of samples for each measurement point was 3,000. The ambient noise was measured by a line area of hydrophone, which was vertically ranged via a buoy located at point NB in the following figure. It is noteworthy that during the field tests, the sea conditions, especially the wind speed, at the sea surface were recorded. In what follows, the performance of proposed algorithm is evaluated by using the mentioned experimental data in the Strait of Hormuz. As an example of evaluating the performance of proposed algorithm, experimental data of the Strait of Hormuz are utilized. As a result, a useful formula is obtained for calculating the absorption coefficient in that region. As illustrated in this figure, under different scenarios, there are significant differences between measured data and the results of FG formula under the same conditions for the frequency range of 10 to 100 kHz. Accordingly, utilizing FG formula in the Strait of Hormuz is not efficient. Therefore, in what follows, by utilizing the field measurements in the Strait of Hormuz as the appropriate inputs of TFGF algorithm, a suitable formula is obtained for the absorption coefficient in the Strait of Hormuz. As the output of the TFGF algorithm, the above figure illustrates the parameter P2 in terms of depth. As obviously seen, approximate care and measured data provide an excellent match. As a result, equation 4 is proposed as a tuned form of FG formula for the frequency range of 10 to 100 kHz in the Strait of Hormuz by considering some constraints for temperature, salinity, and depth of water. In other two figures, the experimental data are compared with the outputs of proposed formula and the outputs of original FG formula in the frequency range of 10 to 100 kHz. As obviously seen, under two different scenarios of data acquisition, there is a significant gap between our findings and the outputs of original FG formula under the same conditions, whereas the proposed formula and experimental data provide an excellent match. It is noteworthy that, similar to this example, one can consider the appropriate sound speed profile and experimental data of any other interest region. Then, by utilizing the TFGF algorithm, a suitable formula is obtained for that region. The main contributions presented in this talk can be concluded as follows. Number 1. The main goal of this study was addressing a simple method for tuning the parameters of absorption coefficient formula in the seawater based on the experimental measurements of any interest region. Number 2. The performance of proposed algorithm was evaluated by the experimental data of the Strait of Hormuz. Results of this research could be good guidance to study considerations for the deployment and operation of physical layer of underwater acoustic sensor networks. At the end, this research is dedicated to my teachers, the 175 immortal divers who were martyred in the imposed war and holy defense in the Islamic Republic of Iran in 1986.